Good morning. Happy Monday. Hope you all had a good break. Today we have a short lecture on lasers, and that'll be the end. And then we'll do a review Kahoot, which is super long, like 13 questions, but it's based on the homework, so it'll help you prepare and find some of your weaknesses and strengths so as you study for Wednesday's exam. And so let's dive in. So electronic spectroscopy, of course, they have microwave lasers and infrared lasers, but the most impressive ones, even the laser pointers, those are all in the visible range, which deal with electronic spectroscopy. So this is a suitable place to talk about lasers in the curriculum. And so today we're going to talk about lasing action and what are the requirements to produce a laser. And then lasers have really revolutionized spectroscopy because they're what we call spectrally bright. They're very narrow in the wavelengths that they put out and very bright in that narrow band. So they produce a lot of energy in a very narrow package spectroscopically. So as far as a probe of a system, electronic system, it's really like a small pointer or almost like a scalpel. You can send that light in, you know exactly how much energy you supply to the system, and then you can look to see what happens to the molecule after you hit it with a laser. And so you can see emission events and so on that are very precise using a very precise source. So in terms of a laser, we're looking at a radiative transition. And so these different transitions that we have for all lasers, either electronically, like a diode laser, or a pump laser where you pump it with light, you have some excited state, and then that excited state reaches a radiative level, and then you want efficient radiation in terms of the lasing action. So we're probably dealing with something fast like fluorescence. And so we'll have a fluorescence transition, not a phosphorescent transition for a laser. And so we'll be dealing with not the full potential energy surface or even the Jablonski diagram. We're just going to talk about energy levels, but these would be electronic energy levels. And on top of that would be implied the vibrational and rotational energy levels. So the energy levels that you see today are going to be electronic energy levels, and they'll just be single lines. And so this is a particular system, the neodymium YAG laser. And so this is a good example of what we're talking about. We have an efficient pump. So that's this line right here in terms of the lasing action would be a pumping, and we think of what is a pump? Well, you know, like a water pump, you're pumping water up to a higher potential energy. So you're pumping it uphill, pumping it to a higher reservoir, or pumping it into a pressurized environment. In terms of lasers or light spectroscopy, we're pumping the molecules to an excited state. And so we're taking those molecules and we're trying to excite as many as we can in a small amount of time. So we have a bright source pumping those molecules to an excited state. And then we might have some fast non-radiative relaxation down to what we call a metastable state. That just means a state with a short lifetime, and it's or say moderate lifetime. If it's too short, then you don't get a population inversion. But what we really need is this particular thing. It's a population inversion, so you can put a star by that. If you can't get a population inversion, then you can't have a laser. And because this is not going down to the ground state, this particular system is very good for making a laser, because we have an efficient pump. So we pump the molecules up to this excited state and they relax down, and so then you end up with a lot of molecules in this excited state. And essentially no molecules here. You have a lot of molecules down here in this state. So this state is full of molecules. So there's a lot of population down in the ground state. We've pumped a fair number of those molecules up into that metastable state, and then there's zero molecules here. And so you have a huge population inversion. So what happens when this first molecule drops down in energy and emits that photon? That photon comes out and immediately interacts with one of these others and stimulates another emission event, which sends its photon over and it hits another one, and then that stimulates an emission event. So when you have this population inversion, you have the opportunity for stimulated emission. one molecule dropping down matches that energy exactly. The selection rules match, everything matches for that transition. And if there's a lot of molecules in that upper state, that photon doesn't escape without stimulating the emission of other molecules. And so coming out of this system, we have a lot of photons that are in phase with each other. And so that's the light amplification part of a laser. So thermal equilibrium is exactly the opposite of what you want. So in that top example, we have thermal equilibrium. We might have one excited molecule and the rest of them are in the ground state. This would be the Boltzmann population. So Boltzmann population of molecules is the thermal equilibrium. That's how you would tell if you were at thermal equilibrium. Population inversion simply shows that you have more molecules in the excited state than you have in the ground state. Here we have 5 molecules in the excited state and only 4 molecules in the lower state. And let's say, so as soon as that molecule drops down, that photon of light stimulates the emission of another, which stimulates the emission of another, and you see eventually you have this bright source of light coming out. And that's the light amplification by stimulated emission of radiation. So it's the first photon that stimulates the second photon, which stimulates the third, and they're all in phase with each other. So you can think of it as a bright wave coming out with a huge amplitude, or a lot of photons coming out. So really the research into lasers is, can we get the energy levels to be the right distance apart for the spectroscopy that we want to do? So if we want to do visible spectroscopy, we need those energy levels to be like 20,000 wave numbers apart to get it into the visible wavelengths. If we're doing mid-infrared research, we want something in the 400 to 4,000 wave number distance. And so if we're doing radio waves, we need really, really low energy differences. And so the research comes into finding systems that have the energy spacing that we want that can also give us a population inversion. One of the first lasers ever made was the Ruby laser. And so we have this bulky, water-cooled, high-voltage power supply, which runs electrical current through a particular gas in this glass tube. So this is kind of like a neon light, only it's white. It's just, we're pumping a lot of current through this gas, and it's white light. And it's pumping this ruby crystal up into an excited state and getting a population inversion. And then if you polish both ends of that crystal, or if you put it between 2 mirrors, then you have a resonant cavity, and you can actually build those wavelengths up, and it'll ring kind of like a rod. If you hit it with a hammer, it'll ring like a tuning fork. And you put these mirrors on either end, and you can build up that light in phase. And then one mirror, if it's just partially silvered, then the light leaks out that end. And so the light that's leaking out is the laser. And so we're pumping that resonant cavity, and if we want to pulse the laser, we can build up the light and then let it out in bursts. And those are your most powerful lasers. And the ones that we had in my research at Oregon State were Q-switched. And so if there was light that came out that was of the wrong polarization or in the wrong direction, it would leave the resonant cavity. And we would only build up this standing wave of bright light, and we'd let it out every, we did 10 hertz, so 10 bursts per second, and the width of the burst was 10 nanoseconds. So all that light would come blasting out in 10 nanoseconds. It was only a millijoule or so, but when you deliver it in that short a period of time, it's megawatts of power. So the molecule was feeling a wave that had the power rating, the joules per second of megawatts. And so that's why I was saying it's extremely bright for that molecule. We could shake that electron cloud like crazy and get Raman spectroscopy out of it. So that was the Q-switch laser. Nowadays we have these diode lasers, and they've really transformed everything, because if you look at the periodic table, all of the metals and the metalloids are available for making these light emitting diodes. You think about all the LEDs that you've ever seen, all those different colors. and you can tune them by putting in a little bit more arsenic, a little bit more gallium, a little bit more germanium, and play with the electrical potential in those diodes, and you can get a slightly different wavelength. And then you can tune that wavelength by making the crystal a little bit larger, a little bit smaller. And you can even change the temperature of that and sweep the frequency a little bit. Just like a particle in a box, if you make the box bigger, then the frequency differences get smaller, and you can create a longer wavelength pulse. And so this is all of the different pieces to a light emitting diode. This P and N here, these are P-doped and N-doped aluminum gallium arsenide crystals. So if you take this substance, what is N-doping? Well, you're doping it with something that has a little bit more electrons. So if you look up here, you see gallium, germanium, arsenic, and aluminum. You see the arsenic over there. If you put a little bit more arsenic into the crystal, you're giving it more electrons. And so that would be N-doping. If you give it a little bit more aluminum or a little bit more gallium, you're essentially inserting holes, compared to germanium. So you see how they kind of sandwich around germanium? You can make a silicon or a germanium crystal, and you could put in arsenic atoms to give it a little bit more negative potential because it has extra electrons. Or you can put in gallium into that crystal and have holes, missing electrons. So the gallium acts very similar to germanium, but it's like germanium with one less electron. And so that would be more positive because, again, you've got sort of an exposed nucleus, one less electron. And so this N and P doping allows you to change the potential of those crystals just a little bit and modify its electrical properties. And so you can read more about this. I got this picture from the Britney Spears Guide to Semiconductor Physics. I just thought that was funny. I don't know. So the guy says, leave Britney alone. Okay. And now, if we go from this diode laser, which is this tiny little diode laser, and you see up there the scale, here's the diode laser next to a penny. And so this is the diode laser inside there. So you've seen LEDs, they're so tiny, okay? You take that LED, light emitting diode, put it between two parallel surfaces, and you have a diode laser. You can take that high purity light and amplify it, and amplify it, and amplify it. And they start with these diode lasers, and they get up. This is a picture of the largest laser in the world. Lawrence Livermore National Laboratories. This is the National Ignition Facility, and it's a fusion research laser. So they take that diode laser and amplify that light. So that's another thing that you can do. Remember, it's light amplification by stimulated emission. So if you take this laser and you send it through another crystal that's got a population inversion, the light gets amplified. You bounce it off and pump those crystals back up and send the light back through, and you can amplify it more. And you send it back through, amplify it more. And you can just keep doing this and doing this. The only thing that limits this is your ability to keep the light focused in a column. And so those are just macroscopic optics. You just have really high quality mirrors and high quality lenses, and you can do fusion with lasers. So that's what this facility is. Let's watch a video on this. I'm going to stop the recording though because this is copyrighted. So.